Okay. Is my voice okay in Zoom and YouTube? Shall we get started? Yeah, let's get started. Good afternoon, everyone. Welcome to another lecture of the Digital Design and Computer Architecture course. I'm Mohammed Sadr, a senior researcher working with Professor Mutlu. The reason today I'm giving lecture on behalf of Professor Mutlu is that Professor Mutlu now he is in China for a keynote speech and awards ceremony. So I will do my best to cover this lecture in a good way. Let's see. So today we are going to see more details on pipeline processor design. Mostly we want to see how we can handle data and control dependence using, hardware and software solutions. And also we will try to cover at least partly the exception handling, precise exception handling. So this lecture is going to be quite interesting. So let's get started. So as you know, last week and today we are still in the pipelining part. Today, as I said, we are going to cover control and data dependence handling and also precise exception. And after Easter break, we will cover out of order execution, which is, quite interesting topic because, most of, modern processors, they are not in order mostly. So they are using out of order execution to, basically they are implementing kind of data flow machine inside the processor. So the readings for this week is, again, pipelining, which is, you can see here, and also pipelining issues. And also the reading that you can have for this week and also after Easter break is, you can see in this slide as well for out of order execution. So as a quick review, we cover pipeline data paths and control. And you know that basically the control logic in a pipeline processor is similar to basically a single cycle processor. The difference is that control signals, they should be delayed to proper pipeline stages, as you, I guess, already know. So, and in pipeline, because the life is not all, beautiful all the time, at some point we need to stall the pipeline, and the stall is a condition when the pipeline stops moving. So, and there are multiple reasons for that, such as resource contention that you actually covered. You saw that in the previous lecture, and also dependence between instruction that can be data and control, and some, long latency operations. Like, you will see also later today for exception handling, and also some other stuff later, like caches. So whenever you are accessing a memory, you can access a fast memory called cache, because you may have the idea of cache memory. So, and basically sometimes you miss in cache and you need to access the long latency memory, and then you can encounter long latency operations. So the data dependence type, we actually, these are a kind of review slides, so I'm gonna go over them quickly. So we have a read after write, which is, flow dependence, which kind of true dependency that basically is kind of the first instruction or earlier instruction is going to produce a result, and later on you're going to consume that result. So basically you have to wait. And this dependency is it is also a dependency that we need to consider in data flow machine. So because in data flow machine also you cannot start an execution once your input data is not ready. So true dependency, which is read after write, we need to basically handle it in a good way. But there are also some other dependencies like anti-dependence that's basically write after read. So, and you know that for this and also output dependence, these are kind of false dependency because you can handle them by just renaming the registers if you have enough number of registers. And you will see more about register naming in later lectures, basically in out of order. So yeah, so flow dependencies, which is read after write, are more interesting and challenging. And we saw we have kind of 6 fundamental ways of handling flow dependencies. So in the previous lecture, we mostly discussed how we can detect these dependencies so that we can stall to make sure that we don't, basically execute wrongly. But today we also see how we can improve the performance. So again, here is a very quick review. In this example, so there is instruction I that is going to calculate something and produce, store the result in register Rx. And this register is going to use for instruction J later on. So there is a kind of dependency between 2 instructions. And in the basically instruction ordering of the compiled code, these 2 instructions are completely continuous. So the distance between them is 1. So if you execute the pipeline like what you can see here, basically you are gonna produce wrong result because register X is not ready here to read. So in order to handle this, you need to wait as a stall, just to make sure that you have the results in the write back stage and for the instruction I. So you need at least this destination between 2 instructions should be at least 4. So in order to handle that, you can add no operations in the compile time. So in your compiled code, you can have some no operations between these 2 continuous instructions just to make sure that I'm not doing anything wrong. And also you can, compiler can also do better and make more intelligent code by finding kind of independent instructions and reorder them and put in the between of these 2 instructions. But we will see also later more. But here you can also have bubble, and that bubble can be actually implemented in hardware. So the compiled code can be easily what you can see here, but at the hardware side, basically the pipeline processor need to push bubbles to the pipeline so that to make sure that you are waiting for that data. So this bubble is, it's kind of to implement the stall. And the stall, basically, the formal definition is to make the dependent instruction wait until its source data value is available. And in order to do that, basically, we need to stop all upstream stages like fetch and decode. And also, we need to drain all downstream stages or flush the pipeline. Just make sure that we don't have active instructions in the pipeline, that they are not operating on up-to-date results. So now let's see how we can, implement stalling a bit more. I guess you are already aware of that. So in order to implement stall, we need to disable program counter and also this latch between the instruction fetch and instruction decode, IFID latching, and ensure basically stalled instruction stays in its stage. And then you need to basically insert invalid instructions or kind of no operations into the stage following the stalled one, that we call them bubble. So later stages or downstream stages, they should be considered as invalid instructions or that you push bubbles. So let's take another look as an example here. So we have one instruction that we want to write to register S0. And next instruction, read this register. So we have kind of read after write dependence. So here, for example, the add instruction writes into S0 in the first half of cycle 5. Consider that we have this internal forwarding in the register file. I guess Professor Mutlu, he has already covered that in last week's lectures. The register file can provide that internal forwarding, such that you basically write into the register file in the first half of the clock cycle, and then the second, the rest half of cycle you can read from that register file, and you have up-to-date result. So imagine you have that support here, so you can basically for the add operation you can write into S0 in the first half of cycle 5, and then there is another instruction, and that basically needs to read this S0 in cycle 3. So which gonna obtain the wrong value because their data is is going to be available at cycle 5. An OR instruction needs to read this data in cycle 4, this OR. And this is also going to be a wrong value. The subtract instruction needs this value in the second half of cycle 5, and it's going to be correct value. So in order to make this code correct, we have to basically add 2 no operations or no ops after add and basically AND instruction, or insert 2 bubbles, let's say. So basically, we should make sure that we are not doing the wrong thing, and these no ops, as I said. So these no operations are costly because, I mean, you are not doing, you are just waiting, and you are not doing a positive, I mean, useful stuff, because, I mean, no operation in the end is no operation. So it's not going to basically proceed the execution of your program. So in the end, I mean, as I said, compilers can also act more intelligent and try to find some interesting and independent instructions such that they can reorder them and put them between these 2 instructions, just act them as a useful no operation, let's say. So, but we can also do much better in the hardware that we are going to discuss about data forwarding. So data forwarding, also called data bypassing. The idea of data forwarding is that we want to forward the result value to the dependent instructions as soon as the value is available. So this idea, I guess, reminds you another processing, let's say, principle. Any idea? So we have already seen this basic idea before in data flow. So in data flow also, you can basically fire the instruction once the all the inputs for that instruction is ready. Basically, there is no delay as much as needed for one instruction. But here, I mean, we want to implement that also with forwarding. Once we produce the output, which is not after write back. So the output basically can be also after ALU, after execution stage. So when you have the result, you want to basically communicate that result to the next, I mean, dependent instructions, such that they can also proceed and they can they can be executed. So that's the idea for data forwarding. And basically, as I said, I mean, data forwarding brings the pipeline closer to data flow execution principle. So in the end, is a kind of implementing principle. I mean, architecting following principle design. But data forwarding comes from at some cost. I mean, it's not free. It's very important to improve the performance, but at the same time, it comes at the price of some costs that we will see today in lecture. So let's see 3 specific forwarding paths in this example. So here, I mean, we are again, we have the same example that we had in before in past slides. So we have this add instruction that's gonna basically store the addition of S2 and S3 inside S0. And there are 3 instructions later on that they all need the value of S0, right? So after actually the execution stage, which is, you can consider it, you know, the latched output of ALU, or you can also consider at the beginning of the memory stage, right? So this is the memory stage. So here you have the result, right? So if you make some forwarding path such that you can communicate this value from the latched output of ALU to input of ALU, then this instruction actually can operate without any stall, and actually can operate with a true value. Also for this OR, we need the value here, which is, you can see we have conflict. I mean, this add operation will be in this stage, which is in the beginning of the write back stage. So if you again communicate the result of S0 from beginning of the write back stage to input of ALU, you can also operate on this instruction without any delay. And then we have also this subtract instruction that we already, supported with providing internal forwarding in register file. As we said, we can write to the register file in the first half of cycle, and then we can read the next half of cycle. So for this one, we, implicitly supported that. But this is also a kind of forwarding path, which is implemented as an internal inside the register file. So any question so far? Okay. So here also you can see these for forwarding paths pictorially. So the one of them is from latched output of ALU to input of ALU. You can see this forwarding path. You need to add multiplexers because, not all you need to add multiplexer or increase the number of inputs of multiplexers, by the way. So because, the inputs of the ALU can come from the forwarding path. So these red lines show the basically forwarding path for the two source operands that you can have in ALU. And this orange one is for the write back to input of ALU. And for the register file, these two lines. So these are how we implement forwarding paths in a pipeline processor. So basically, so in data forwarding, we forward to execute the stage from either memory stage, which is memory stage is the latched output of the ALU, and from the write back stage, beginning of the write back stage. So then we have this question, when should we forward from either memory or write back stage? So basically we have one criteria, important one, which that if that stage will write to a destination register, and the destination register matches the source register of the, future instructions. Basically, in that case that you are going to have read after write dependency, you need to basically communicate these results such that you can proceed. And also, sometimes it is possible that both the memory and write back stage, they contain matching destination registers. So you have kind of, one instruction that you want to store in R1, R0, for example, S0 for the MIPS terminology. And then the next instruction, you want also another operation that you want to also store the result in S0. So basically, in that case, both the memory and write back stage, they contain matching destination registers. So in that case, memory stage has priority to forward its data because it contains the more recently executed instruction. Imagine the order of instructions. So you have one instruction, which is, let's see again here. Yeah, you have one instruction here, for example, that you want to write to S0. And imagine that we have also another instruction, bottom of this one, that you also want to, write to S0. Then we have this and or and subtract operation that they all want to read from S0. So the thing is that, naturally you want to have the, basically you want to forward the S0 value from the second instruction, which is hidden here, imagine, to these instructions, right? Because that's the up-to-date one. So you need to consider that also. So we always basically, prioritize memory stage to the write back stage when you want to forward. That's a very important criteria. So you can also see here in your book, this is the basically pseudocode from your understanding. That's basically how we do the forwarding. Basically, if you need to, you have a source register in your instruction. And this source instruction is basically equal to the write register that previous instruction is gonna. Hello. Okay. Thank you. Thanks a lot. Happy Easter. Happy Easter. Thank you. Okay. So, I mean, later on in this lecture, we are going to see exception and interrupt handling. And it's a perfect example of how we can, receive interrupt. In this case, the interrupt has the highest priority, let's say. So we have to basically service that immediately. Okay. So, yeah, basically, when you want to decide when to forward, you need to basically check some conditions. Basically, you want to, you have a source operand, and also this source operand is equal to the register that you are going to update. You have the value of that in the memory stage, and also this register write m. In the memory stage, you have something, active. You have active value that you want to write in the register. So in this way, basically, you are going to forward from the memory stage. You can see that we first check this one because it has the highest priority. And then else if otherwise, essentially the same thing, but the difference is that you are checking for the write back stage. And in that sense, you are going to forward from the write back stage. And then basically, otherwise, no forwarding. And this is how we implement basically data forwarding. So data forwarding is very good to improve performance, but unfortunately, it's not always possible in pipeline processors. That's a kind of strong word to say it's not possible because, when you're designing, almost everything is possible, but you need to always consider the trade-off and your principal design. So in this example that we're going to see soon, if you want to implement the forwarding, you are going to increase the clock cycle time a lot. So that's going to violate your basically critical path delay principle. So let's see. So you have this load word instruction. That's basically this code is essentially the same as the previous one. The difference is that you are gonna, instead of having an R type instruction, you're gonna have a load word. So the output is gonna calculate it after the memory stage. So you don't have the result of S0 in the memory stage, because you need to, in the memory stage, you're gonna access the memory and read the value, and then in the basically in the write back stage, you have the value. So the next instruction, and which need S0, you can see that it needs the value in the execution, and basically in the execution stage, and basically you don't have the data right now. So in order to basically implement that, you can forward the output of the memory to the basically to this to the input of ALU. But that means that you are lengthening the critical path, because Then in the critical path, you should consider the memory and also the forwarding path and the ALU, because all of them is happening in combinational kind of circuit. So that's the reason that basically forwarding is usually sufficient to resolve read after write data dependency. But sometimes in some cases when forwarding is not possible or is not efficient to implement, I would say that's the more accurate term. So due to pipeline design and instruction latencies. So the load war instruction does not finish reading data until the end of the memory stage, and its result cannot be forwarded to the execution stage of the next instruction, unless you basically increase the critical path latency, which is not a good thing to do. So in this case, basically this instruction needs to wait for at least, I mean, in this example for 1 cycle, because in our simple pipeline design, we consider that we have 5 stages, and each stage has, I mean, takes only 1 clock cycle. So essentially you need to, I mean, wait 1 cycle. But in real pipelines, in modern processors, the pipeline depth is much, much higher. And basically that's sometimes we need to install more. Okay. Yeah, and this is exactly what we see. So we need to install this instruction since we don't have the result. And then later on, we can actually continue. So 1 install would be enough here. Okay, so basically we have kind of a stalling and dependence detection hardware. This is kind of review because you already seen that. We have, we have some signals from this dependence detection logic, like flush, and also stall D and stall F. So we already covered that. Basically, whenever you want to stall, you need to make sure that fetch and decode stages, they keep the current instruction, and the current instruction is not, or let's say the stalled instruction. And this stalled instruction is not going to move. So basically you need to, you should stall them with these 2 control signals. And the later downstream stages, you need to flush the pipeline. So because of that, you have this, I mean, flush, which is kind of invalidated, let's say, instruction. So stalls are supported by adding enable signals to the fetch and decode pipeline registers, and also synchronous reset clear to input, clear input to the execute pipeline register, or an invalid bit. I mean, there are different ways of implementing that. So way to implement basically this stall handling. So again, when a load word stall occurs, we need to keep the values in the decode and fetch stage pipeline register, and which means that we need to assert a stall D and a stall F. And then we need to clear the content of the execute stage register, introducing a bubble or flush execution. This is actually flushing is the terminology from your book, which I mean, I would recommend that you also check that to, I mean, learn these materials in more detail. Okay, so now we are done with the data dependence handling. We want to see a special case of data dependence, which is control dependence. So control dependence is essentially data dependence, but the difference is that your dependence happening on the instruction pointer or program counter. So we have this definition of control dependence. So we are asking this question: what should the fetch PC be in the next cycle? So the answer would be simple: the address of the next instruction, of course. But the thing is that all instructions are control dependent on previous ones. So basically, your normal, let's say, R-type instructions, the next instruction always is PC plus 4, right? So then basically the address of the next instruction is dependent on the previous instruction. You need to add the PC by 4 such that you can read the new instruction. But imagine the next instruction is, the current instruction is kind of branch, like BEQ or BNE or jump. So basically, the address of the next instruction is dependent on the outcome of that branch. So in BEQ or BNE, which are kind of conditional branches, depending on if you are going to take the branch or not, you're not going to take the branch, I mean, taken or not taken, you basically will have different output. You will have different next instructions. So when it is not taken, the next instruction is essentially PC plus 4. But when it is taken, you are basically, you need to calculate the next instruction using relative addressing, right? Because in BEQ and BNE, I mean, the next address of the instruction is calculated by the current BC and some offset, which is relative addressing. And also for jump instructions, you know that that's unconditional jump. You're gonna take that branch for sure. But the thing is that the output of that jump, or for example, jump register, you don't know that unless you execute that instruction. So the target branch address is something that you need to execute the instruction such that you learn basically the next PC. So that makes actually this control dependence a bit high, a bit hard to solve. So and also there are some ISAs that they have different lengths of instructions. So in MIPS, for example, we always have 4 bytes instructions. So you always know that the next instruction, if it's not, I mean, the current instruction is not branch, is PC plus 4. But there are also some ISAs that they have different lengths in instructions. So, I mean, and then you don't know basically how many bytes you need to read. And there are also some ways to handle that. But for simplicity in MIPS, we are considering fixed lengths. I mean, MIPS actually consider fixed length instructions. Okay, I already covered this. So basically, as I said, if the instruction that is fetched is a control flow instruction, which is branch or jump, how do we determine the next fetch IPC, instruction pointer or program counter? And actually, we have also another issue. How do we know whether or not the fetch instruction is a control flow instruction? So in the fetch stage, you fetch an instruction because you're fetching, but basically you don't know if it is control flow instruction or R-type or anything until the decode stage. So basically you don't know what you want to do for that. So essentially you are you can predict that, oh, okay, I'm gonna predict that the next instruction is PC plus 4. And I'm gonna fetch PC plus 4. But at some point I will realize that, oh, this is the wrong instruction I'm executing. So I need to flush all the instructions that I already executed. And that brings, cause some performance issue. So this actually brings us to branch prediction, which is, a special case of data dependence, as I said, dependence on PC. So imagine for BEQ, so conditional branch is not resolved until the 4th stage of the pipeline, which is after the execution stage. So you can actually have a prediction, simple, as I said. Imagine that we have always not taken prediction. So whenever, no matter I am executing branch instruction or not, or let's say non-control flow instruction, I will always gonna fetch from PC plus 4. So that's prediction that you are doing. But this is also called always not taken prediction. But at some point you will see that this prediction is wrong, which is misprediction, that you need to flush all the instruction that you were executing them in a wrong manner. So, and that brings us to basically branch misprediction penalty. So the number of instructions that you're flushing in your pipeline, that is your penalty that you're paying. And this penalty, actually, we are gonna see that in the MIPS processor is not, let's say, that high, using some forwarding paths and technique that we are gonna see soon. But in modern processors, actually, because the number of stages of the pipeline usually is quite deep. So this basically misprediction penalty is quite high. So that's really important to avoid misprediction penalty. So in MIPS and also in modern processor, in order to reduce this misprediction penalty, people are using early branch resolution. So let's see. So this is our pipeline so far, that we have only forwarding paths for data. So this is this instruction that you can see as an example. BEQ is gonna compare T1 and T2, and this is the offset for the next instruction. if your branch is taken. And there are also some instructions in later instruction pointers, 24, 28, 2C, which they are in hexadecimal basis. And this is a 6.4, which is basically the destination of your branch. So if this branch is taken, you need to go to this instruction to do the SLT operation. So as we consider and assume, we will have always not taken prediction. So you're gonna fetch from the PC plus 4. So you will basically fetch 24, 28, 2C. And then later on in basically in a stage after this, the result of branch is here. So in this stage, you will realize that, oh, I'm gonna take this branch. So all of these stage instructions that I'm executing them is wrong. So I need to flush these instructions. And then that means that basically you have bubbles in your pipeline. So you need to flush all of them and then continue with the correct execution paths. So that's the thing, that basically in order to reduce this overhead, people are doing consider early branch resolution, which is we need to calculate branch target and condition in the decode stage, which is basically we need a separate hardware to, for example, for this BEQ, you need to compare these two registers, right? To realize that if I'm gonna take the branch or not. So usually, the previous pipeline, you need to do that comparison inside the ALU, which is in the execution stage. But in order to resolve this branch earlier, you need to do that. This is how we can do. We need to add a logic inside the decode stage so that you can see that this is equality logic, that you need to basically compare these two registers to basically resolve the branch earlier. And also this logic here is to calculate the branch targets for this instruction. So that's the thing. In order to reduce the overhead of misprediction in branches, we need to do early branch resolution. And for that, you need to add hardwares. And you can see here. And actually, that's not the only the only overhead that you are paying. You also need to consider something else to make it happen. Any idea? In order to make sure that this hardware works correctly, you need to also add something else to this data path. So imagine your branch instruction. So your branch instruction has two source operands. And basically you need one of these source operands can be dependent, or two of them can be dependent on the previous instructions, right? So you have the forwarding paths in the previous slides that you make it happen that you have the up-to-date results for the execution stage, right? But you don't have forwarding paths so far for the decoder stage, right? So in order to make it happen, completely, you need to also make forwarding paths to the decoder stage. And we will see also later quickly. Okay, so with this early branch resolution, we have only one instruction that we need to flush, because that's you have also anyway you have some delays, and that cannot be, because you already fetch the next instruction from PC plus 4. But basically you reduce the overhead from 3 instructions to 1, which is a good thing. So as advantages, basically it reduces branch misprediction penalty, which in the end it reduces CPI, which is cycles per instruction. So, but it has disadvantages for sure. Potentially it increases the clock cycle time. We will see also later. One reason is because of the forwarding paths that I just discussed, and also these logic here. So you have this equality check. So you need to consider this also, the delay of this equality check in your critical path delay also here. So in the end, you will increase the clock cycle. But that's also, we know that basically it's gonna, this early branch resolution is gonna increase the critical path latency of the decode stage. But we don't know that basically if that stage is the longest stage in your pipeline, because the clock cycle of the pipeline is dependent on the stage that has longer latency. So basically we need to calculate later on to see if that increases the latency, increases the clock cycle period or not. So, and essentially you're adding more cost due to hardware. And these hardware that we add, you're gonna use only for branches. And branches are not so common in your code. They are kind of 10%, 15%, 20% of your instructions. But the thing is that the overhead of branches are quite high. As I said, in also modern processor, because the pipeline is quite deep, the overhead of misprediction is quite high. So you need to basically you need to implement early branch resolution to make sure that you are not paying so much overhead. So the performance analysis basic as a quick recall. So the execution time of a single instruction is CPI times clock cycle time, right? Which CPI is the number of cycles it takes to execute an instruction. And the execution time of an entire program, so we need to have a metric, which we call it average CPI, which is the average CPI clock per instruction for all instruction of that program. And then in the end, the number of instructions times average CPI times clock cycle time is gonna give you the overall execution time of your program. So we will want to see more about this. So this is the data forwarding for early branch resolution that I also mentioned. So you need to have another forwarding path from the memory stage to basically to the decode stage. And that causes longer latency here, because this is the combinational latency. And this is how we can implement forwarding and installing hardware control. I'm not gonna go over these codes in detail, but overall what you need to do, basically you have kind of forwarding logic that you're gonna decide what to forward or when to forward. And also you need to have some stalling logic that basically realize when we want to stall. And then you have kind of stall signals that when basically these signals are basically calculated based on these two stall variable, not variable, signals. So basically, as I said, in the full forwarding pipeline, we will have only stalls for load word instruction. Basically, we cover all other stalls with our forwarding paths. So basically, you will have this load word stall or branch stall. So for branch also, we have one cycle stall. But as I said, I mean, this code is quite, I mean, dependent on our example. But in reality, you need to design and see. So this is the final pipeline MIPS processor, which you have in your code and your book, sorry. And basically, it includes always taken branch prediction, or maybe always not taken, I guess. An early branch resolution and forwarding path and a stall logic. Okay. So for the branch prediction, we consider always not taken. So we always predict that the next instruction is PC plus 4. But basically, this is probably is not a very good prediction. Can you guess why? So imagine your programming. You are using one, let's say, code block in C++, for example, or any program language, which is quite useful. You have 4 loops, right? True. Exactly. Yeah, basically in our code, we have mostly, I mean, not mostly, but I mean, many of your branch are kind of backward branches that essentially you need them to implement for loops or any kind of loop. So for those branches, I mean, the output is mostly taken actually. So when you predict that the output of branch is, I mean, the outcome is not taken, you are gonna, I mean, disregard all of these for loops. So basically, in reality, we are doing much better in modern processors. And they are basically have kind of, the complicated branch prediction that basically can reduce the misprediction penalty. So one of the basically also interesting technique is to use machine learning methods also. So in order to, because I mean, branches, as I said, they are really costly, although they are not so common in your code, but the performance overhead of misprediction is quite high. So in order to make accurate result for the outcome of branch and also to estimate the target address for the branch, people are using sophisticated techniques. And one way is to actually use machine learning methods like perceptron that, I mean, there are some prior works that they are doing that. So you will see about branch prediction in your branch prediction lectures later, but that was kind of, to give you some idea about how important it is. But if you are not, basically, you don't want to wait, you can actually go on and watch branch prediction lecture from, I mean, previous editions of this course. But I want to give you some example here. So imagine in this particular example, if your branch prediction accuracy is 99%, which is good, no? You have only 1% inaccurate result. In the end, you are executing 20% extra instructions in this particular example. And if your branch is 90% accurate, you are executing 200% more instructions. So you can see that actually the accuracy of branch prediction is quite important, and it's important that make it as much as possible accurate. And these are also some slides from that branch prediction lecture. And some lectures from the past on branch prediction. If you are interested, you can watch now, but we will also cover it later in this course. So, okay. I was planning to cover also this part before the break, but we have kind of Easter break. So let's have a 5-minute break because we already have short break. So let's have 5-minute break and then we can continue with this part. Okay, let's get it started again. So let's quickly see an example here about pipeline processor. So this is an example from your book, I guess. We have an important program consists of, these instructions. This comes from the profiling of your instruction. You have kind of 20% loads, 10% stores, 11% branches, 2% jumps, which are, unconditional, and 52% R-type instructions. And we are assuming that 40% of loads used by next instructions, which means that in 40% of cases, whenever you have load, you need to stall for one cycle. And 25% of branches, we have misprediction. So we need to flush the next instruction on misprediction. And all jumps flush the next instruction fetched. So we always have 2 cycle execution for jumps. So what is the average CPI? So in order to calculate the average CPI, we need to basically calculate the CPI for each instructions. So for load and branch, we know that, CPI is 1 when we have no stall, right? Or flush, for branch is flush. And it is 2 when we have stall or flush, right? So for CPI, the load word, in 40% of cases, you need to stall. So basically in 60% or 0.6, you will have 1 clock cycle. And in 40%, you're going to have 2 cycles. So in the end, the CPI for load word will be 1.4. Similarly, for BEQ, you have in 75%, you have 1 cycle. However, for 25%, you have 2 cycles. So in the end, you have 1.25 average CPI for branch. So the average CPI that we have for the whole instruction is calculated with this equation. So you have 25% of instructional load, and the CPI for load is 1.4. 10% of store, and the CPI is 1. 11% of branch, BEQ. So we also calculated the average CPI, 125. 2% of jump, and the latency for jump is 2, the CPI. And 52% are R-type, which the CPI is 1. So in the end, your CPI is 1.15, which is, in this example, which is not a very bad thing, because, ideally, the CPI for pipeline processor is 1. But here also, we are close to 1. So 1.15 is not a bad thing at all. So, but unfortunately, this is the CPI calculation. But as I said, this is not only about CPI. You also need to be careful about the latency, the critical path latency. So we have 5 stages and 5 different timing passes. So if you check this equation from your book and also the numbers, I'm not going to cover them in detail. But it turns out that decode stage actually is going to be the bottleneck. And it's going to be basically determine the clock cycle. So essentially, this pipeline processor is going to have lower clock frequency compared to multi-cycle processor, right? Okay. So this is the final pipeline MIPS processor that we covered. And this is the basically different delays numbers from your book. And if you calculate, you will see that the clock frequency, basically the clock period would be 550 picosecond. So the CPI is 115, and the clock cycle is 550. So the execution time would be the number of instructions, which in this example is 100 billion instructions. And CPI is 115, and this is the clock cycle. So in the end, 63 seconds is the execution time for your pipeline processor in this example. So if you compare this performance with other processor like single cycle and multi-cycle, you will see that, in your book example. So for a single cycle, then the execution time would be 95. For multi-cycle is 133 seconds, and for pipeline is 63. So you can see actually that pipeline processor here in our example, provides some speed up. 1.5, which is, I mean, 51% higher performance, or 1.51 times better performance. But this is not 5 times. So, I mean, when we actually pipeline our processor a single cycle, what we really want to achieve is, I mean, our ultimate goal is the speed up is 5x, because, I mean, we have 5 stages and each stage is 1 cycle. So in the end, we want to have 5 times speed up. But in this example, you're seeing that basically your speed up in the end is 1.5, which is much lower than our ultimate speed up. But this is the case. I mean, that's normal in pipeline processors due to the the overhead that you need to add for those registers, like the setup time, hold time, and also the combinational logic, forwarding paths. All of these things can actually increase your combinational latency, which is, I mean, the critical path latency. So in the end, your clock period is not going to be 1/5 of the clock period of single cycle processor. That's one thing. And another thing is that your CPI in a pipeline processor is not perfectly 1, as we also just saw. So in the end, you're going to have some speed up, but it's not that huge. But it's, I would say, it's large enough such that, I mean, all modern processors are pipeline. And as I said, the pipeline is quite deep in today's processors. Okay, so basically, we covered a part of these 6 fundamental ways of handling flow dependence. One other way is that basically we detect and move it out of the way for independent instructions. I'm not going to cover that in today's lectures, but essentially it's a job for the kind of a compiler to find basically independent instructions. And also it can be also happen in the hardware from the out of order execution, but you will see later also in the later lectures. And another way is to predict the needed value, which is, I mean, kind of value prediction. Whenever you are in a read after write position, you can predict the value that you need and basically speculatively execute. But in the end, you need to verify. And if you did the wrong, basically the correct thing, then you should be happy. But otherwise, you need to flush whatever you already did. So this is also we are not going to see. But we will quickly also discuss about do something else, which is fine-grained multi-threading. But before that, I like to, I mean, we have to have some, let's say, critical thinking on basically where should we handle these things, in hardware or software? Basically, what is the role of the hardware versus the software in data dependence handling? So we can have software-based interlocking or hardware-based interlocking, which as you already, I guess, learned from previous lectures, MIPS processors, they were supposed to be completely, I mean, software-based interlocking, but quickly they realized that it's not possible. I mean, because of the huge complexity, and in the end, all MIPS processor, they are using also hardware-based interlocking. And actually, in reality, in today's modern systems, we have both of them. So compilers are quite smart and intelligent, and they are doing what they can and improve your code. You have many optimization passes in the compile time, and also you have hardware-based interlocking and data forwarding passes, such that you can also handle these things in hardware. So, but there are some important questions that basically you need to find the answer for them, but I'm not going to actually provide, let's say, concrete answers to all of them, but yeah. So who inserts or manage the pipeline bubbles? So if we are gonna basically, we are gonna use hardware bubbles, or we are gonna use no operation in the software, or who finds the independent instructions to fill empty pipeline slots? So is this the job for the software? I mean, the compiler, such that find the independent instruction and bring them in the to basically in the between, I mean, to use them as the no operation instructions, or this is the job for the hardware, which is we will see later in out of order execution lecture. Or what are the advantages or disadvantages of each? I mean, we need to think of performance equation as well. So basically, whenever you are doing these things in the hardware, you have more ability to do these things because there are some information that you know them actually in the hardware. We will see later also, we will discuss them. But at compile time, some of these information is not ready and basically compiler, they cannot completely resolve these issues. And in the end, they need to, they need to add some no operations or stalls. But at the same time, when you are doing at the hardware, you need to add complexity. And that complexity causes that you have longer clock cycles. So in the end, you can see that we have a trade-off here. So if we push everything to the hardware, maybe that's not the right thing to do because your clock cycle is going to be long. And if you are doing everything in the compiler, then that's also maybe not right. It's not the right thing to do because compilers they don't know all the things. So as I said, the combination of these two can be more, let's say, interesting. And for branch prediction, as I also discussed, compiler can also provide some hint to the hardware. For example, compiler can inform the hardware by some annotation that this instruction is a branch, and this branch is backward branch. So usually backward branches are going to be taken mostly. So then your hardware can predict that as taken. You can see that basically some information and some hints that come from the programmer or from the compiler can also improve the performance. So, and basically, when we are doing software-based instruction scheduling, we have static scheduling. And when we are doing hardware-based instruction scheduling, we have dynamic scheduling. So you will see this hardware-based instruction scheduling later in out-of-order execution, after Easter break. But so when we are in static scheduling, basically, you have your compiled code, and that's the scheduling. And then basically in the hardware, you need to obey that sequential instruction ordering that you have. So, and all of these, the design, they have impact on the different metrics like performance, complexity, power consumption, reliability, cost, and so on and so forth. So when we are in the static scheduling, basically hardware executes the instruction in the compiler dictated order. And this, you can see the contrast, basically you can contrast this with dynamic scheduling, that hardware can execute instruction out of the compiler specified order, which you will see later. And how does the compiler know the latency of each instruction? And that's the thing. So whenever you want to resolve these issues, pipeline issues in this compile time, basically your compiler should know more detail about your ISA, about the implementation of the ISA, the microarchitecture, because normally compiler does not know that. But when basically that compiler needs to know more, and basically to realize that how many bubbles basically we will have, or how many instructions are going to be stalled. But there are also some information that the compiler cannot know them, or it could be difficult, let's say. Any idea? It's basically some information that you don't know them at compile time, and you know them when you are executing your program. So a general answer to that is anything that is determined at runtime. But there are some examples, like, for example, variable length operation latency. So there are some, instructions that they can have different variable lengths latency. For example, for your multiplication, in our baseline pipeline that we see, so we will have, we had only one, let's say, cycle for the execution. But we will see more complicated pipelines soon. So basically, the latency of the instruction, the execution unit can be different from different instructions. So whenever you have a multiplication, for example, if one of your input is 0, then the outcome of your multiplication is 0. So you don't need to basically wait a lot for that multiplication. But if none of the inputs are 0, you need to basically spend the time for the multiplication. And then the multiplication latency can be, 5 cycles or 10 cycles. Also, as I said, for the memory accesses, sometimes you're going to hit in the cache then you will have quickly have your data, but sometimes you are going to miss in the cache and you need to access your memory, slow memory, main memory. So with these, we have variable lengths and operation latency. And also we have memory addresses. So some of these memory addresses, which is kind of indirect access, addressing. So you need to calculate the effective memory address with the register, the value which is stored in a register, right? So the value for that register is not determined in the compile time. So basically, compiler cannot say for sure that, for example, that memory address is going to be, for example, I don't know, 100, for example. And also the branch direction. So compiler can guess that this branch is going to be taken or not taken, but for sure cannot say, I mean, 100%, I mean, correct result that, and can actually be inaccurate. So as I said, I mean, compiler can provide some hint to the hardware with these things, but there is no way that compiler makes the perfect decision. So people are using kind of profilings whenever they are profiling basically when they want, during the compile time, they can profile, which can be statically or dynamically, such that, I mean, a compiler can test the program with some sample input to realize, okay, what's going to be the behavior of these applications, and then make some decisions. At least that can increase the accuracy for the pipeline, for the compile time decisions. But as I said, it cannot be 100% correct. So you always need to be considered that compile time solutions, usually they are conservative. So because they cannot be 100% sure about the accuracy of the decision. So, but as I said, I mean, that input set that you're going to profile your code is also very important. If you are profiling your code on an input set that you are going to use in the future, more or less, then you will have more accurate results. But if you're going to use some input set that you're not using them, then, or partially using them, you may have some bad, let's say, learning and decisioning. So, yeah, I've also quickly mentioned that there are also some compiler that basically here in this figure, you can see the control flow graph of an application, which is the path of the execution of a code. And during the profiling, compiler realized that most of the time, let's say, I don't know, 95% of the moments, we are using this path. So the compiler is going to fully optimize this path because it's going to happen in 95%. But also consider some ways to, if the program, I mean, takes other passes, what's going to do. But since we will be in this path in 95, for example, cases, 95%, we will basically optimize these to make sure that we have good performance. This is also, I mean, the information that compiler can have from the profiling. And these are some lectures that you can also watch if you are interested. We will also see more about compiler in VLIW lectures later on, but you can also watch them. Yeah. So also recall about the semantic gap. So basically how close instructions and data types and addressing modes are to high-level language. So this is HLL, which is, I mean, can be your C++ programming. And this is the ISA that you have. If the ISA is really close to the hardware control signals, basically you have large semantic gap. And for this, it's hard to map basically HLL to ISA. And more work for software designer and compiler work, basically. And in this case, usually hardware design optimization is quite, I mean, basically we have less work for hardware design. And most of the optimization is happening in the software part. But there is also another way that we can have ISA, which is close to the high-level language, and you have large ear gap to the hardware control signals. So here you have easier mapping of HLL to ISA and less work for software designer. But we have more work for hardware designer, and optimization burden is mostly on hardware. And in reality, actually, many designs, they are using combination of them. So you can have also something like that you are basically compiling your code HLL to a, let's say, high-level ISA, which can be x86-64. And then you have also, since you are, for example, the cores that you are going to use in your system, they are ARM cores, for example, and ARM has a different ISA. You also need to basically translate what you're already prepared for x86 to ARM. And that's also another translation layer. So you can have optimization in all of these levels. You can have some optimization here, some optimization here, and also something here. So basically, in reality, we have both of them. So combination of them. And this idea is actually has been used in different systems in the past, like in Rosetta, and also in NVIDIA Denver. I'm not going to read all of these sentences. You can actually read also later if you are interested. But it's always good to know that basically the history. So this idea of having them that's used in NVIDIA and also in Apple is also, I mean, the key insight, I would say, happened much earlier in 2000 in transmeta processor, that you have a layer of x86. You can see the higher level is 86, but we have basically VLIW engine here, which basically you are having low-level ISA that you are compiling your code with that. And if you are interested, I would suggest that you watch this lecture also. Okay. So now let's quickly jump to do something else, which is fine-grained multithreading, which is something that we have we are using that in GPU design, for example. So what is fine-grained multithreading? Basically, the idea is that we want to fetch from different threads every cycle, such that no two instructions from a thread are in the pipeline concurrently. That's the idea for fine-grained multithreading. So you don't need to basically check for the stalls, I mean, for dependency, and install your pipeline, because the instructions that you are reading in your pipeline and they are working, they are independent completely. Why? Because they are from different threads. And if those threads should not be actually dependent on each other, for sure. But if that's the idea, if you can actually have multiple threads that they are completely independent, you can basically enjoy this hardware. So in order to make it happen, basically you have fine-grained multithreading, which means that you need to quickly context switch between threads. And context switching in normal systems actually is a kind of quite costly, because you need to copy the context of your thread, which is the value of the register, architectural registers, PC, and also other stuff, to the memory, such that when you want to go back to this program, you can basically resume that. But here, since you want to quickly switch between the instructions, you need to basically have the context inside the hardware. So you need to have multiple program counters, for example, or you should have basically registers per thread, a number of registers per thread. And that's one of the reasons that basically why fine-grained multithreading is quite costly in hardware. But that's actually a very good idea. And as I said, GPUs are heavily using that. So threads are completely independent, kind of, but I mean, in reality, it's quite hard to find completely independent threads. And at some point, they may have some, let's say, dependency. So, I mean, there are also some dependency control in real hardwares for that, like GPUs. But the thing is that the amount of hardware that we have, for example, in GPU for dependency control is much lower compared to CPU, for example. For example, you don't have probably forwarding passes in GPUs. So, yeah, as I said, no instruction is fetched from the same thread until the prior branch instruction from the thread completes. You don't need to add logic for handling control and data dependence with the thread, and you will have high thread level throughput. But then you have also some issues. One is that your single thread performance would be low, because I mean, you're going to switch between multiple threads. So you're increasing the execution time of one thread. but at the price, I mean, for providing basically overall high throughput. So we are going to provide high thread level throughput, but we are increasing the latency of single thread execution time. And you need to have extra logic for keeping thread context, as I said, and you will have throughput loss when there are not enough threads to keep the pipeline full. That's also very important to note. I mean, for example, in reality, you should have, for example, 16 threads in your design, since, I mean, consider your pipeline has 16 stages. And in order to make sure that you don't have stalls, you want to have at least 16 threads. But there can be some cases that some of these threads are not active because, I mean, they are waiting for long latency operations like accessing memory. And accessing memory can happen like 100 cycles. So at some point, basically, you will run out of active threads and you need to stall the pipeline. So you will have kind of throughput loss, which is actually happening also in throughput processors like GPUs as well. So here, we are showing as a, I mean, kind of as a pictorial example. You are seeing different colors, which means that you are running a different. I mean, in these instructions, we have 5 different instructions, and each of them are with different threads. So that's how we are implementing fine-grained multi-threading. And you need to basically increase as I said, the number of PCs and register file. So, and yeah, that's the idea. And so another way to basically think about fine-grained multi-threading is that you want to tolerate control and data dependence resolution latencies. So for one thread execution, sometimes you will have some dependency latencies and also branch resolution that you need to wait. So you want to basically tolerate or kind of hide that latency. And how is happening by overlapping the latency with useful work from other threads. That's the idea, basically. So that actually significantly improves pipeline utilizations and improves thread level throughput. So there are 2 examples, for example, here from the past in CDC 6600, which is, I guess, one of the first or maybe the first out-of-order processors. So this processor executes a different I/O thread every cycle, and an operation from the same thread is executed every 10 cycles. So, I mean, you can imagine that they consider 10 threads. And this is another example for another processor that we have 120 threads per processor, and you have some, I mean, available queue versus unavailable waiting queue for threads, and each thread can leave only one instruction, can have only one instruction in the processor pipeline. And in the end, each thread is independent. So, and to each thread, processor looks like a non-pipeline machine, right? So when you consider for each thread, you need to wait for the whole pipeline to be finished such that you can you can execute the next instruction. So to each thread, processor looks like a non-pipeline machine. So in the end, you will have much higher system throughput, but single thread performance is not good, as I said. So this is also, I mean, a pictorial example of this machine that the cycle time is 100 nanoseconds on that time. And you have 8 stages, which is, I mean, 800 nanoseconds to complete an instruction. So assuming no memory access. And basically you can schedule instruction after instruction for each thread after 800 nanoseconds, kind of. Okay, and this is an example of implementation that you need several program counters and also several registers. And this is also another example. This is how we need to basically increase the number of PCs, and then you need to have a multiplexer to select which thread you want to fetch, and also the basically thread select logic. So whenever, I mean, depending on the instruction type, misses in the caches that you will learn later on. And also if we are having interrupts or traps that we were planning to cover, but I guess, let's see. And also resource conflicts, you may not, you will decide which thread is gonna be considered to execute or scheduled for the execution. Okay, and basically you need to increase the register file and instruction buffer. Okay, so for fine-grained multithreading, as a very quick recap, so we don't need to basically to use dependence checking between instructions. Only one instruction in pipeline from a single thread we have, and there is no need for branch prediction logic. So otherwise, bubbled cycles used for executing useful instructions from different threads. So, and overall, you can improve system throughput, but you provide latency tolerance and pipeline utilization. However, it has also some disadvantages. So one important one is extra hardware complexity, and you will basically reduce single thread performance. So one instruction fetch every n cycles from the same thread. And as I said also, resource contention between threads. So in real life, we may not be able to find completely independent threads. So in the end, you should have some logic to make sure that how you want to handle resource contention. For example, what's going to happen if two threads are going to access the same bank of the main memory or the same memory memory address or something like that. So in reality, you need also to use some logics like that to handle these contentions. And you will have also, you will need some dependence checking logic between threads may be needed. So for load or store. So as I said, the amount of logic that you need for fine-grained multi-threading is significantly lower compared to other kind of implementation, but you need also some support for that because you will have some kind of this contention also in reality. So modern GPUs are fine-grained multi-threading machines. This is an example for NVIDIA in GTX 285 core. I mean, in NVIDIA terminology is SM that you will learn also about, I guess, we will have lecture for GPUs later on also. So here you can see actually we have 64 kilobyte of storage for thread context, the register file. So that's the reason. I mean, as I said, for fine-grained multi-threading, you need big register file and you need also multiple program counters and such that you can basically make fast context switching. And today is actually, I mean, GPUs are more complicated. For example, I guess the latest GPUs, H100, I guess it has a 256 kilobyte of register file per core, which is, I mean, huge. And that's also not the only thing. I mean, there are also some papers that they are showing that we need much higher register file also. So in reality, you need to increase the register file even more. And in this architecture, you need you are running group of threads, which 32 threads. In NVIDIA terminology is warp. And basically you have up to 32 warps in this old, let's say, GPU architecture. In today's NVIDIA, I guess we are running 64 warps in one SM. And the number of SMs here, for example, number of cores here in this architecture is 30, but today GPUs mostly they have higher than 100 cores in their die. So you can see how many, the total number of threads that we have. So imagine that we have 100 cores and each core can run 2K threads. So in the end, you will have 2000 K threads. And the amount of register file is also per SM is 256 kilobyte. And you have more than 100 SM, so you can see how large is the register file for such systems. Okay, yeah, I mean, these are also some further learning if you are interested. So, and for multi-threading, I mean, we cover up to now multi-threading for the performance-wise, but that's not the only thing. I mean, multi-threading can also have basically functionality in different domains as well. So imagine that you want to provide reliability. So one way to provide better reliability is that, for example, you are running a single copy of your instruction or your program. You're running 3 copies of that program in a, let's say, in a fine-grained manner. So in the end, you are producing results from 3 threads, and you are going to basically vote them. And then you're doing majority voting to basically make sure that, okay, if one of the threads are gonna, for some reason produce wrong result, at least I have 2 other threads that they are producing correct result. So you will provide better reliability. That's also one thing. There should be also other ways, a reason to use multi-threading that you can actually also watch this lecture and learn more if you're interested. And these are some lectures on multi-threading. Okay, and now we reach to this part. I'm planning to also, for the remaining time, at least start this part because it's good to think about it during your Easter holiday. But for sure we will have this lecture in the next, after Easter break, and then out of order execution, hopefully. So in a multi-cycle execution, basically not all instructions take the same amount of time in the execute stage. This is actually, in reality, we have something like that. So we have multiple different functional units in the processor that they take different number of cycles. For example, you do basically fetch and decode, and then you depending on the instruction that you have, you may have different latencies. If your instruction is a simple addition, your latency is going to be only 1 cycle, for example, in the execution stage. But if it's a multiplication, usually multiplication is more costly compared to addition. So you need to wait 4 cycles. Or if you have floating point multiplication or also floating point addition, they are going to be also more costly. So in the end, in the system, modern system, we have multiple functional units. And depending on your instruction, you're going to have different latencies. So should it and these basically a stage can be pipeline or not pipeline. So in reality, we are usually pipelining them because it doesn't make sense that, for example, we imagine that you are have only these 2 instructions. So if you don't pipeline them, you need to wait always 4 cycles, right? The latency of, let's say, 4 cycles for the addition. However, you can basically pipeline your multiplication such that you reduce the clock cycle time, such that you can actually work with higher frequency, which is good for your performance. So we usually actually also pipeline our ALU. And in modern processors, ALU is heavily pipelined. Yeah. So whenever, when this operation, this kind of implementation, make it happen that, for example, when you are decoding one addition instruction, you are executing that, but the next instruction, for example, is multiplication. You are not occupying the whole ALU for that. So you can actually go to that integer multiplication and use that unit to, execute. Or also, while you are operating on an integer multiplication, you receive another, let's say, addition. So you can actually proceed and run that because you are using different functional unit for addition. So in the end, this processor design can heavily increase your throughput. So here we are seeing an example. So instruction can take different number of cycles in execute stage. And we have basically here, we are considering integer addition versus integer divide. So you will have, for example, one division here, an example, and then addition and some instruction in between. And then you have division and addition here as an example. So this is how, for example, we are now executing. That we basically fetch, decode, and then we have few cycles for the execution of this division, and then we have write back. And then we are gonna do fetch, decode, execute, and write back for this addition. So do you think such execution is correct, or there is some problems with that? Any idea? That's the hint. I mean, think of von Neumann architecture. Are we obeying here the semantic of the program, the sequential semantic here? So you are basically finishing or retiring or committing these instructions out of order. So this division instruction happens before addition. So it needs to be finished basically before this addition. But now you are saying that we are doing write back here, but before that we are doing write back for many of these instructions in the middle. So that's wrong. So basically sequential semantics of the ISA, we don't preserve it here. So basically we don't obey the contract between the ISA and the microarchitecture. So, and actually this problem can be even worse. We can have in your division, you may have some, I mean, one of the input, I mean, the one, you can have a 0. So division by 0 happen. So in that sense, we will have, I mean, kind of exception. I mean, normally we can have sometimes division by 0, which if you run some C++ program, for example, you saw that sometimes you have runtime error, right? That, for example, when you're dividing by 0. So these are kind of exception that can cause much longer latency, or I mean, completely finish the program. Or the thing is that so when you want to, for the programmer, when you want to get back to this code and realize what's going on, so this instruction happens, the exception. But the thing is that we already also write back these instructions. So the architectural status of the processor, which is communicated to the program, it's not clear that actually what was the problem, right? Because when the program checks, oh, I mean, this addition has been done, okay, the next instruction also finished, then what was the problem? And there also can be some instruction before this that we didn't basically finish them, exactly because that we didn't obey the ISA. So these are the things that we shouldn't basically let to happen. And these are some exceptions, basically. And you also need to basically realize them, and basically you need to wait. And then at some point, you need to basically handle that exception. These are some pictures that maybe we can, with some examples here, we can wrap up today's lecture. So these are pictures that I guess Professor Mutlu, he took last year. So here at that time, 12:55, you can see that for some reason, this tram is stalled. That could be a power shot for some reason, power off. And then there is another tram that is waiting because of the commission of the waiting that this instruction is stalled. And some cars also, they are waiting here. So this is an example of exception, right? And here you can see that this tram, actually, that was a reason that we have some exception, that this tram at 2 minutes later is still waiting there. This is another picture that this tram is still waiting. This is another picture that that tram is still waiting. And I mean, sometime later, exception causing instruction. I mean, now exception handled and resolved. So basically, and then basically we handle the exception, and then we can continue the normal process. So this is not a perfect, let's say, analogy for what we are looking for, because I mean, trams are different, let's say, programs, but we are now considering the same program. So one good thing to think about for your Easter break is that we have kind of exceptions that they are kind of internal to your program, like division by 0, or for example, when you have overflow in your execution. But also we have some external events that need to be handled by the processor, like what happened, like the people that came to the lecture for giving Easter gifts. So these are kind of interrupts, like the input I/O. For example, someone enters some numbers on the keyboards. So these are interrupts that you need to handle them. So they are external events. And basically, exception and interrupts are kind of, they are handled similarly in the processors, but they are different. And it's good to think about the difference between them, because in the end, that happens that if you really think about that critically, you can better handle them. So with that, I'm gonna, stop here and wish you a nice holiday and see you all after Easter break. Take care.